But Jakub's going to share with us for the next 20 or so minutes his understanding around deep learning, language, technology, and the accelerating future. Please put your hands together.
Thanks, Johnny. So it's indeed true that I'm, strictly speaking, work in the recruitment industry, selling semantic recruitment technology, but I won't be doing that today. And thanks, David, for the introduction to neuroscience, because I'm going to continue a little bit in building upon that, talking about artificial neurons. The topic that I want to bring to your attention today is something called deep learning. If you're only working in recruitment and social networks, that might not have caught your attention yet, but it's a very exciting set of developments. In my original area of background, I have a research background in AI and machine learning and language technology, and really in the last few years things have started to completely speed up, hence the term accelerating future, in terms of the type of technologies that are being developed. Companies like Google, Facebook, Apple, Microsoft, Amazon are massively investing in these new type of deep learning technologies, and I'm going to just take you through a tour of some examples, and I hope you will get the idea that really something exciting is going to happen. The accelerating future, well, that's always this kind of phrase. There are people like Ray Kurzweil who argue that within a few years we'll have the-singularity. And there's a whole kind of religious following to that, based on the argument that we have Moore's law, right? Computers getting doubling in speed every 1.5 years or so, and in a number of years they'll simply surpass the computing capacity of the human brain, and that's when machines will become more powerful and kind of take over humanity, unless we get ourselves uploaded somehow. So I don't particularly subscribe to that view. I think we can be a little bit more modest about the technology progress. But I do think that in the recent years, and especially in this deep learning area, there is a sense of accelerating of going towards a very changed future. And there's this famous phrase by the science fiction writer William Gibson, who says, "The future is already here, it's just not evenly distributed." Well, we are in the Barbican here, and actually a 15-minute walk from here is the original office of DeepMind, a company that has been acquired by Google quite recently. And I'm going to show you a little video of work that they published in Nature earlier this year in February. And what you're going to see is not some very fancy graphics, it's actually very old school. You're going to see a video game, an Atari video game from the 1980s. And what they built is an agent, a completely self-learning agent that is teaching itself to play this game. So after about 200 episodes, still fairly miserable, drops the ball here and there. This is a game of Breakout. The goal is to destroy all these blocks. After around 400 episodes, it's actually learned to catch the ball pretty efficiently. It's doing about at the human level, and it's able to destroy these blocks. A really amazing thing happens now. After being trained for 600 cycles at this game, the self-learning agent actually discovers the optimal strategy, which is to not bounce the ball back and forth, but actually every time shoot it into this hole so that you make efficient use of this environment. And it's able to do that so accurately that when the ball comes back, it immediately throws it back in. So it's performing at a level better than most, let's say, good human players of this game. And not only have they been able to train a machine without any knowledge of this game to do so well, they've actually done this for all the classic Atari games, Pac-Man and Space Invaders. Some of you might still know them. Why is this really amazing? the only input that this learning algorithm is getting is the pixels that are on the screen, so the colored blocks, and the final score. Everything in between it figures out for itself. So let me take you through some of the building blocks of that. Basically, there's this field called machine learning, which has exactly the same, namely to teach computer systems to learn something, right? To learn from examples how a certain behavior should be performed without being programmed, without having rules that tell them what to do. So the two components for that is data and a certain perspective on the world. So the typical approach is supervised training. So there are manually labeled data. So you could think of, for example, distinguishing cars, pedestrians, and bikes in a collision detection system, or classifying cases of bank transactions as fraudulent or not, or some kind of classification tasks. And then there are examples of real data of that. And then there are features or signals which kind of tell the algorithm what measurements to take, what dimensions of these data are relevant for making that decision. Well, the data is then fed into an algorithm. There are many different algorithms with cryptic names like support vector machines and hidden Markov models and conditional random fields. Forget all about that. And then basically it's kind of iterative method. You then take new data which was not labeled, or where you have held back the labels, and you compare how well is the algorithm doing, improve a little bit, add more data, add new features, and repeat. So that's kind of the classical machine learning approach. And you can visualize this a little bit in terms of a space where the data are points in some space, and the dimensions of this space are the features. So for example, here we want to distinguish the red points from the green points. One is a set of cats and the other are dogs. So we collect examples, we measure these things. The features are here height and weight. And the algorithm tries to learn a boundary between the green dots and the red dots. And you can make a very simple decision boundary, a line, or you can make it very complex, and there's a whole science behind that. The problem with this approach is that, one, you need humans to label a lot of data, and two, you actually need to think very hard, what are the right features? How do I distinguish cats from dogs? And that's kind of a black art. It's very time consuming, very iterative. You need very smart data scientists to do that. What if it becomes kind of more difficult and we want to distinguish cats and dogs, but the inputs that we have are bitmaps, it's just photographs? What kind of features are there to be found in photographs that really make this line in this very high dimensional space? Well, coming back to the neuroscience part, we as humans don't actually get taught like that, right? To make a distinction between cats and dogs, you have to pay attention to, the form of their tail and the shape of their ears. We just learn it from examples without being given the features. So that's where we come back to the neuroscience. There's this whole set of algorithms that are kind of loosely inspired by the neuroscience, and that model these type of decisions as networks of simple cells that are connected by kind of synaptic connections with a weight. And these weights are adjusted, as David showed you. And then based on a certain set of inputs, all of these cells make their little computations, weighting their connections and deciding whether to fire or not. And then in the end, in the final layer, it kind of goes from that side to the output layer, there's a decision. Is this a cat or a dog, for example? And this is not a new set of techniques. Actually, it was very well studied in the 1960s already. And then there was a kind of second wave of a lot of interest in this, in cognitive science and AI in the 1980s. But it never really took off at that time. nobody could really get it to work on interesting problems. Well, one of the main reasons is that, coming back to Moore's law, computers were really, really slow. So like a scientific supercomputer was probably slower at that time than what you have today in your pocket. And there is a big breakthrough. Probably none of you know exactly what this is, but if you have a 15-year-old nephew who's into gaming, they will know. This is a graphics card. So there's been a kind of explosion of computing power becoming available for everybody, because one such graphic card that you put in a common PC has many thousands of cores compared to maybe 4 or 8 cores that your normal processor has. So all of a sudden we have this explosion of computing power, and people have started to try again to model these kind of neural networks on this new type of hardware. And this is called deep learning. So what's the idea? Why is it called deep learning? Well, the idea is that you make a very deep network. So here is your decision that you want to learn. And here is, for example, the bitmap of the photograph. You make many, many layers, and apart from the computing power, the advance in the technology is also some tricks to how to actually make this process converge and how to train all these separate layers independently. And one of these tricks is also that you can use unlabeled data. So you can just feed, for example, photographs to such a network and ask it to compress them and then uncompress them again. And in that process, without any labeling, it will learn interesting features. And building on top of these features, like little face detectors or edge detectors or contrast detectors, you can then build representations which are relevant to your problem that you're trying to really solve, which you're solving in the final layer. So here you see an example of the type of representations. So we're feeding photographs to the network. In the first layers, it will develop automatically by learning these kind of visual detectors of contrast and edges and things like that. Here already kind of in the middle upper layers, you see little features like wheels and doors that are important for distinguishing different cars. And here in the final layer, you will be able to make a decision like this is an Audi or this is a Mercedes or this is a bicycle or a pedestrian. And of course, if you feed it very many different types of images, it will develop a more a richer representational repertoire. So it will develop receptors for things like faces and cars and animals, elephants, chairs, all of that automatically by just feeding it images. Okay, sounds magical. Let me show you some more nice examples. And all of this is fairly recent work, 2013, 14, 15. A lot of this coming out this year from research at Facebook and Google and similar companies. So distinguishing cars from bicycles or pedestrians might be a very useful task. But we kind of could already do that with traditional machine learning. It was maybe a little bit more difficult. What if we try to learn some completely different concept, like artistic style? So what these people have done is an article that just came out August this year. They basically fed images from different painters to such a neural network. And with a certain set of tricks, they forced it to recognize which painter a certain image was from. And now they've got all these different painters represented in this network. And what you can do now is feed a photograph into this network and stimulate some of these nodes that are associated with the concept of these styles. And the network will automatically transform this photograph into a Van Gogh, into a Munch, into a Picasso, into a Kandinsky. It's pretty neat, right? Another example. And you should try this out on the web because you can actually upload your own pictures. And this is a neural network that Google is using to tag images and videos on YouTube. So it has seen basically all of the all of the photographs and videos that Google has digested. And these researchers did a really nice trick. You can now upload your own photo that you made, and they will add just some random noise to the network where the representation gets kind of disturbed. And what you then start to see, I don't know if you can see it back in the room, is that the network will start to hallucinate. It will basically add dreamlike structures, kind of psychedelic texture to your images that's kind of taken from somewhere else. Little towers here in the landscape, waterfalls, all kinds of stuff. Okay, so that's playful. A little bit more useful. These deep neural networks can be actually used to label images. So if you have a lot of visual material, you can get different cells in the network that stand for different concepts. And of course, these can be trained by crowdsourcing. So you can just give the task to a lot of people, say, what's in this image? It's a chimpanzee. And then the network will learn the concept of chimpanzee to distinguish chimpanzees from gorillas, for example. So that's all visual recognition. And the little video I showed you in the beginning is also a recent application by DeepMind, as I told you, of these type of techniques. And what they do is really, as I said, take the raw bitmaps from this game and feed them into this kind of deep network, and then just use the score at the end of the game as a reinforcement signal. So there's no classification task. It's a bit more complex. It's called reinforcement learning. So the network actually decides on how, let's say, the success at the end of the game should be attributed to particular moves that it made during the process. And here, you should look it up in this paper. It's published online. It's a kind of brain map of how this network has made representations for these type of strategies, like bouncing the ball behind the wall and then letting it ping pong there. So it's really accelerating in this last year. There are tricks to make these networks structured so that they actually model focus or attention. So you can have this bitmap that's fed in, but you can actually train the network to kind of zoom in on particular parts of that image before it processes another part. And in research at Stanford by Andrew Karpathy, he actually used this method of attention plus a recurrent neural network, so that one that has a kind of a sense of time, so it knows what it had been doing before and what it's going to do next, to take images and actually output captions. So here you see this picture, and the network will say, these are two young girls that are playing with a Lego toy. It's not 100% correct, it might not be Lego, but it's pretty amazing. Or this boy is doing a backflip on a wakeboard. Man in blue wetsuit is surfing on a wave. Man, that's pretty... you can just input any random picture. It will make mistakes. If you look at that URL, there are also some very funny mistakes there. But that's something that certainly nobody could do last year or the year before. So let's move a little bit to language technology. Obviously, we were interested in language in recruitment because we have a lot of language data, right? CVs and jobs. I'll spend a few minutes, a few seconds on that later, but just a few examples of how you can apply this not only to images, but to text. So this is a project done at Facebook, where they feed the network a simple story. John is hungry, John goes to the kitchen, John eats an apple, Daniel's hungry. Where does Daniel go? The network will be able to answer to the kitchen. It's something that is not written in the story, but it's inferred from the, let's say, the representational state of the network after reading this story. A football fits in the suitcase fits in the cupboard, a box of chocolate is smaller than the football. Will the box of chocolates fit in the suitcase? Yes. So that's not a complete question answering system, but it's a kind of a couple of toy examples that show that in principle these networks are capable of digesting a text, a story, and showing fairly intelligent behavior on the basis of that. Other advances in language technology, there's speech recognition. It's been worked on for about 40 years now. With these deep neural networks, engineers are now able to throw away all of that work and just take the sound signal of a very complex language like Chinese, which is a tonal language, and just map directly to text without telling it what the kind of the linguistic units are, whether there are phonemes or words or sentence structure. Machine translation. So the actually Google Translate is already using this type of technology, and there are huge advances being made. Used to be a lot of linguists involved in machine translation, writing grammars, writing dictionaries. Turns out this is not necessary anymore. Benjo and others have basically shown state-of-the-art machine translation performance, or even beyond, by just training a neural network on aligned text, so text that is available that you have the translation for. So zooming in a little bit on this language stuff and going towards a little bit of recruitment, some work that we are also doing at the Textkernel. It's an approach called word-to-vector. So basically, if you're processing images, you already have high-dimensional data, right? So every pixel in the image is a number. But if you're processing text, you have characters. So first we must find a way to translate these linguistic units, the words or the characters, into numbers. And word-to-vector is an approach for that, where we basically use such a deep neural network and try to predict words that come around a particular word. So we just take a lot of unlabeled text, hundreds of millions, 100 million or more words of text, and we just learn for every word to predict the words that are situated next to it. And obviously, because similar words will tend to occur in similar contexts, the network develops a kind of meaning structure in its internal representation. So you will see that there are certain, let's say, spatial relationship in that space, where, for example, you can do kind of subtraction and addition. So you can take, for example, the vector of king, the word king, and take kind of the stretch of road that you need to travel in that space to get to the word queen. Okay, so you take this little thing here, and then you take the plural of the word kings, and you apply the same distance here, and you should actually arrive at the plural of queen. So really a lot of language and meaning relationships are preserved in that space. Another example of that, here you have countries and their capital cities. So what's that got to do with recruitment? In our work, we apply it, of course, to textual data from CVs and jobs. So we feed in lots of unlabeled CVs and jobs. And then we get little nice clusters for cities, for job titles, for skills, for education, for competences, for activities. Not sure if you can read this, but you actually see that the vector for coach is very similar to the vector for mentor or trainer or instructor, teacher, tutor. It's of course very useful when we try to meaningfully process textual data in HR. So here we see a space where we distinguish names, the red ones, and they are in a different part of the space than job titles, obviously. And here we have organization names. The problem in CV and job data is, of course, there are a lot of unknown words. There are a lot of words which you haven't seen before. And using these large sets of unlabeled data, you can basically learn the meaning of those words without telling the computer what to do. So, coming back to recruitment or, say, the labor market, I think we all realize that the language gap between the applicant and the organizational language used to describe the job is kind of where a lot of waste is going on, where a lot of disconnection are. People will talk in very different words, and for both sides it's a kind of guessing game. Obviously Johnny teaches people how to play that guessing game very well, but I think the future is kind of trying to build that bridge automatically. So that's what we're working on at Textkernel with this team, and I hope you enjoyed the examples and also get a feeling that really something special is going on in this area. And I'd like to take up the discussion over lunch with you on how this might change recruitment. Thank you.